Hello, good morning, students. In this situation of coronavirus, I am starting home lectures. In a video lectures, I am going to broadcast this, and in this topic, we are going to cover this unit 4 of your bridge engineering. That is design of hydraulic and structural designs of piers, abutments, wing walls, approaches, and so on. The regarding brief discussion of bearings, joints, articulation, other details, and the bridge foundations, various types, necessity investigations, and design criteria. Well foundation. I have given some ideology that you need to study this through your books you have, and these are going to discuss in when you need to join back to the institute. To start with the design of the piers. What are piers? The piers, we have the structures located at the ends of the bridge spans at intermediate points between the abutments. Between the two spans, the structure is where the span is being holded, or you can say where the weight is going to be transferred to the foundation, is called as the piers. So that is the one of the structures. The other, at the ends, we have abutments. Good. Then the functions, we have two functions, basic functions, to transfer the vertical loads to the foundation, to resist all horizontal and transverse forces acting on the bridge. So I'm giving you the brief discussion. You can go through the books with for the detailed discussions with your with figures also. Everything is given in your book, which I have referred to you. Types of piers, we have solid, cellular, trestle, or hammerhead types. Then we have loads and the forces which are going to act on the for the design of the piers. Dead load of the superstructure and the pier, that is the self weight of the pier. Second, live load of the traffic. We have discussed all the classes, class A, AA, 70R, class A or class B loading. I hope you remember all these loadings. Then there is the impact effect, of course, for the top 3 meter of the pier only. Buoyancy of submerged part of the structure, that is, there may be two conditions: dry conditions or the floody conditions. When there is when there is water, there is the water, then you have the condition of buoyancy. Effect of wind on moving loads and on the substructure. Force due to water current, forces due to the water action if applicable, longitudinal forces due to tractive effort of vehicles, longitudinal force due to braking of vehicles. I hope you understand all these. This is very simple language. Longitudinal forces due to resistance in bearings, seismic effects, forces due to collision by barges for piers in the navigation waters. So these are the few loads and which are to be discussed in the design of the piers. We'll start with one of the example of the design of the piers, exactly from your book. Let's see. The data which is given to us is the superstructure, the simply supported T-beam of 21.3 meter span. I mean, actually we need to go for the T-beam design bridge. The few of the data has been taken up from there. We will discuss the design of the T-beam in the class itself. Then the foundation here itself is the well foundation. There are two types of foundations for the piers. One is the well foundation and another one is the pile foundation. Given here is dead load from each span. So there are two spans, let's say, and in between you have a pier which supports 2250 kilonewton from one span. Reaction due to live load on one span is 900 kilonewton. Maximum velocity of the current is given to us as 3.6 meters per second. Class load, live load is this, you have to decide by considering all the classes, class AA, 70R, A or B. Here it is said that class A or AA may be severer. M20 grade of concrete has been taken up for the design. Sorry. Stresses due to dead load, and first case is the stresses. We will be calculating the stresses due to all the loads, and then we are going to compare this with the permissible stresses which are given us as the compressive stress as the tensile stress. So first case is the stresses due to dead load and the self weight. This is the, you can say, figure where we have the section. This is the section of the pier where it is 2700 at the bottom and 1800 at the top. HFL is given to us as 18. This is in elevation 8100, and the overall height of the pier is 9000. Then we have the plan. The plan is something like this. It is 8200 for the straight portion, and then we have the circular shapes at the end. So this is called as hemispherical. Then we have 2700 as the width for the straight portion. So we'll be considering the design for the straight portion. This portion may be neglected. Okay, then so we can calculate the dead load and the self weight from this physical features which are given to us. Dead load from the superstructure There are two spans. So both the spans on one pier will give us 4500 kilonewton. Self weight of the pier. So it will be the average width has been taken, that is 1.8 plus 2.7 by 2 and the height has been taken, that is 9000. So this gives volume of the this gives us the one section cross section of the this into 82, that is 8.2. It will give you volume of the concrete into unit weight of concrete will give us the total self weight of the one pier. Total direct load, that is to be cater itself is so 4500 plus 8 415125, that is 86, this one. To calculate the stress, this total load will be taken up by the base, the surface area at the base. The surface area at the base will be 2.7 and 8.2. So it is 8651.25 divided by 8.2 by 200. So this gives you 390.75 kilonewton per meter square as the stresses at the base due to self weight and the dead load. Now, so on, we will be calculating the stresses and then we will be take the total stresses to compare with the permissible stresses. Second is width of the pier at HFL. Height of HFL is at what level? So you have HFL at 8100. So we need to calculate this width. This section we have to calculate. So I have taken this triangle, and when you compare this, I can find out this distance. So this distance comes out to be 0.9 meters both these sides. 1.8 meter you will have at this level. So both when you add, you come out to be 1.89. You can go through this. So it is 0.9 by 9 into this. This is only interpolation of this triangulation. So this width is how much? This width is 0.45 both these sides. So this comes out to be 0.045 one side. When you add, you get it as 1.89 meters. Then you can calculate the, for buoyancy, you can calculate the submerged weight. That means this is submerged in water. You can calculate the weight of the water. So this gives me volume of this portion as 152.4. 10 is the kilonewton per meter cube is the density of the water. So that gives me a load of 1524 kilonewton, which is acting downwards. So upward, sorry, the buoyancy gives you the lifting. So this is negative effect. So stresses at the base due to buoyancy is again the base surface area, you have it as 8.2 and 2.7, you all know that. So it comes out to be 68.8 kilonewton per meter square. Then I have stresses. Third, I have stresses due to eccentricity of the live load. Live load, already told to us, we are going to cover it through the, this is the eccentricity, sorry. So eccentricity we are going to take from the class A or class AA, whatever. So reaction due to live load from one span is 900, this is given to us, and it acts at 0.45 from the center line of the pier. This I'll show you. So we see that there are two bearings over here. One of the bearing is here, one of the bearing is here. This is the center line. The load is going to act at the bearing. So that means this is an eccentric loading of 450. This is not clear. Let me focus. Yes, now you can see. I'll send you the this PDF also for this, so you can go through that. So this is 450. So load is asymmetric over here. It has eccentricity is 0.45. That is why we have taken for the live load. The eccentricity is moment is 900 into 0.45. That gives me 405 kilonewton per kilonewton meters. Bending equation, I hope you remember. What is that? M by I is equals to F by Y is equals to E by R. So when you take the first two terms, that is M by I is equals to F by Y. When you compare that, you get F as the stress. So stress is equals to M by I is equal to F by Y. So Y, when you take that distance, it gives me I by Y is equals to Z. So I need to calculate the modulus of elasticity. So modulus is BD square by 6. I is BD cube by 12 for a rectangular section. So when you calculate this, it comes out to be 9.96 meter cube. Axis you are going to take at the right angle to the direction of the traffic. So accordingly, B will be 8.2 and D will be 2.7. So you have 2.7 as the depth. Then the stress at the base is what? It is, yes, P by A plus minus M by Z. So this is P, that is the load, live load. A is again surface area 8.2, 2.7 plus minus M by Z. This gives me two stresses, 81.3 and minus 0.1 kilonewton per meter square. So you can keep this. Later on we will tabulate all these forces. Then next one is the stresses due to longitudinal forces. There are two types of longitudinal forces. One is the tractive effort, and the other one is the due to the movement of the bearings due to the temperatures. So due to the tractive effort or braking forces, now they have considered class AA loading. Class AA loading, we know that for the tracked vehicle it is 700 kilonewton. 20% load has been taken up for the effort of braking, so it is 140 kilonewton. Due to this 140 kilonewton, I will be acting at the bearings. So height is 9 meters. So that means here a longitudinal force is acting, which will give me a perpendicular distance of 9 meters, and the moment is going to be released at the bottom is 149 into 9, 140 into 9, that is 1260. Again, so stress at this due to this moment will be m by z. So this comes out to be 126.5 kilonewton per meter square. Next is, in the same case, longitudinal forces we have due to the resistance in the due to the temperature effects of the bearings. If the bearings are going to, both the bearings are going to behave differently, that is unequal efficiency, then there will be some kind of moment generated. So for this kind to look into the effect, the frictional coefficients has been taken as 0.25 and 0.225. 0.25 has been taken upon where the loading is there. If the live load is on the left span, so I have taken that 0.25, and if this is not loaded, it is 0.225. So this gives me something like resistance, total resistance by the left hand bearing. This is the load which is coming out to the 2250 is the dead load, and this is the live load. So total load gives me, for a efficiency of 0.25, gives me a value of 787 kilonewton. This is the resistance caused by one bearing when the left hand span is loaded. If I consider the other span, that is efficiency is 0.225, but there is no live load, so 900 is missing in this picture. So 2250 into 0.225 gives me 506 kilonewton. So difference between this will give me a moment. So I have 281 as the difference between the 2 kilonewton, and again it is going to act at the bearing level. So the moment at the base is 281, that is difference, into 92529 kilonewton meters. So stress at the base gives me 253.9 kilometers due to this second one. So this is the A and B part are the due to the longitudinal forces. Then I have the stresses due to wind load. Due to the wind load, this area, first case, area of the structure seen in elevation due to deck and handles has been taken up from the design earlier before that we are going to discuss in the later classes. So you can just assume that this is 71.7 meters square, or you can just take it to be 100 meters square, let's say. Then average height for the exposed level at the from the bed level is 10 meters. I had discussed one wind load chart with you for the different heights. So at 10 meters we have the load as the wind intensity of the wind load as 0.9 kilonewton. This is given in table 3.2 in the book of Johnson Victor. Total wind force then comes out to be area into the this intensity of the wind load, that is 65.2 kilonewton. Then I am going to calculate the wind force due to three considerations. First is the wind force against moving load considering class A train. That gives me a specific area of 20.4 into 3. This gives me 61.2 kilonewton load as the wind load. Second case is, so total wind case in this case is total wind force, that is 65.2 plus 61.2 plus 61.2. So this comes out to be 126.4. Then minimum criteria for a deck load is, if the intensity is 4.5 kilonewton, then the area has been taken as 23.1 into 4.5. This gives me 104 kilonewton. Third case is minimum mounting force at 2.1 exposed for the surface area. This gives me 170. So we see that among these three, 172 is the higher one. So this has been taken as the maximum wind load at the bearing level. Now so moment at the base will be what? So moment at the base will be the 172, which has been taken from this figure, the maximum load, into 9. So again this gives me modulus of this gives me moment which is going to be taken at the which will give me the stress at the base of this base of the pier. In this case, the modulus of section of the pier will be B, now will be 2.7 into 8.2. 8.2 will be D. What this is the you can say according to the transverse direction which we have taken earlier on, that is the longitudinal axis. So when you go that the physical figure again, so that means we have, B will be this. So wind is traveling in this direction. So longitudinal axis. Okay. Then the stress at the base again, that is m by z. So z you have calculated over here as 30.2, and so you get a stress over 51.2 kilonewton per meter square. Then we are left with stresses due to the water current. The intensity of the, again we have discussed this before when we have talked about the forces on the bridges. It is 0.5 kV square. So you can calculate this. K is also, again, this is the roughness coefficient. 0.5 into 66 into 3.6. V is the water current. The maximum velocity of the water current has been given to us 3.6 meters per second. So the water is going to act for the, again, the volume of the concrete. So it comes out to be 87 kilonewton. And this force is going to act at 2 by 3, you can say. It is something like this. This is a triangular distribution, so it is going to act at 2 by 3, the, you can say, the center of gravity of the triangle. So here this force is going to act at 5.4 meter above the base, and this force will be 87 into 5.4 comes out to be 470 kilonewton meters, and this gives me a stress at 15.6 kilonewton per meter square. If it says the water is not, the currents are not, now the currents are, maybe the currents maybe not be straight, but maybe at some angle, let's say that is theta, and theta has been taken maximum as 20 degrees. So depending on this 20 degrees, there will be two components. One will be f cos theta, which will be parallel, and the other one will be perpendicular. So parallel component gives, when we calculated, it gives me a 4 kilonewton, and perpendicular component gives me, that is in this downward direction, it gives me 1.5 kilonewton per meter square. The stresses due to the component parallel, which we have calculated as 15.6, when we compare this, it comes out to be 14.5 kilonewton per meter square. The force which is acting perpendicular will act on the surface area, that is 8.2 and 8.1, that is the water which is where it is submerged. So this gives me a total force of 99.6 kilonewton. Moment at the base, so base, now it is will be the you can say the horizontal distance, so it is 5.4. so this gives me 99.6 into 5.4, that is 53.8 kilonewton meters. You can calculate the stress m by, you can say the m by z, z, that is 9.96. So sorry, this is 99.6 rather. So this gives me 54 kilonewton meter square. So total stress will be 54 plus the maximum of these two values. This 15.6, yeah, 14 point, sorry, 54 will be added to 14.5, yeah, the maximum 15.6. So 15.6 has been taken, so this gives me 69.6 kilonewton per meter square. Then we have a chart, we will compare these. So they have two conditions. One is the dry condition, one is the flooding condition. So first case, what we have calculated is dead load and the self weight, then the buoyancy, then the eccentricity level load. Dead load for the dry conditions, buoyancy, no water is there, so no stress. Buoyancy is negative in the flooding conditions, so 68.8 we have calculated earlier before. Sorry please. Eccentric live load, either of the two values may be added or may be subtracted. This will be added, this will be subtracted. Longitudinal forces, tractive effort, you have plus minus. So I have written all these, we have jotted out all these stresses which we can calculate here. When we add all, if we add, you get a positive value of maximum, that is 880.9, this is kilonewton per meter square. And for the floods, it is 881.7 kilonewton per meter square. Similarly, when you choose the negative signs, then you have minus 63.5 and minus 201.9. Positive means compressive force, tensile means negative force. The permissible forces, we have chart over there, which gives, if you do mass concreting as the ratio of 1 is to 3 is to 6 mixed by volume, then I have maximum compressive stress 2.7 MPa. 1 MPa actually is 1000 kilonewton per meter square. So that means it makes to 2700 kilonewton, or this makes it to 28 kilonewton per meter square. So when you compare these, so this comes out to be 280, sorry, 2700 and 280 kilonewton. So you have to compare these stresses with what you have calculated over here. So you see, it is 0.88 MPa, and this is 0.063 MPa. So that means we are well safe with these physical features, these physical data with you. So this makes a good check for the design of the Pier. So this is all about design of Pier. Lastly, I want to conclude that a seismic effect may be used, but we are well in, you can say that well in over safe for this. So that means those features can also be taken into account. So this is basic design of a Pier design. Thank you.